Hi everyone, welcome to the London Machine Learning Meetup. So I'm Martin Goodson, I'm from Evolution AI, who are sponsoring the meetup. Today we are joined by Xavier Bresson from the National University of Singapore. As usual, Xavier is going to talk for around 40 minutes and then we'll have a Q&A for around 20 minutes at the end. So please add your questions to the Q&A as usual. So don't use the chat for adding your questions. Add your questions to the Q&A and that way we can track things. Please add as many questions as you can. That's what keeps the conversation really vibrant. So we're really grateful for any questions that you can put into the Q&A as we go along. Just before I carry on, actually, I was going to ask you a couple of questions. So the first thing is, if anyone wants to give a talk or wants to recommend someone to give a talk, someone that they're interested in hearing from, then obviously let me know. Just send me an email, just respond to one of the meetup emails and I'll get it. Or if you want to facilitate the discussion or moderate the discussion, anyone is welcome to do that. Come along and, so if you want to, you can invite someone to give a talk and then moderate the discussion. If it's the conversation that you want to have, please let me know and we'll make that happen. And the other thing I wanted to ask, I was thinking, do you think it would be useful to have a way of communicating with each other in between the meetups? So like a Slack channel, Discord server, or even a subreddit or something like that. Actually, maybe if you can just raise your hand if you think that might be useful. Just a way for us to kind of exchange a bit of knowledge. There's obviously a lot of knowledgeable people in our community, and I think it would be quite helpful to have a way of talking to each other. So just keep raising your. I can see we've got quite a few raised hands. If you just keep raising your hands as I ask Xavier to start, then for the next 5 minutes I'll be counting. After Xavier is given his talk, the Q&A will be facilitated today by Giuseppe and Alessio, who are my colleagues also at Evolution AI. But for now, I'm going to hand over to Xavier. Thanks, Xavier.
All right, so thank you, Martin, for the introduction and the invitation to give a talk. So hopefully you should be able to see my slides. All right, so welcome everybody. So I'm going to talk about the traveling salesman problem and how we can solve this problem using the transformer network. This is a joint work with Thomas Laurent from LMU. So here is the outline of the talk. So I'm going to make a brief history of TSP. I will review quickly the traditional solvers and then the more recent neural network solvers for this problem. Then I will introduce our proposed architecture. I will show how we can decode a TSP solution. I will show you the numerical results, and finally I will discuss and conclude. So TSP. So the TSP is simple to state. So you have a set of 2D coordinates of the cities, and you want to find a tour that starts, for example, from this point and goes through all other cities once and only once and come back to the original city. And you want to find the tour with minimum length. So this was first formulated by the mathematician William Hamilton in the 19th century. And actually TSP belonged to a larger class of routing problems which are used every day in industry, like warehouse organization, transportation, supply chain, hardware design, manufacturing. So TSP, we know TSP is a NPR problem because it makes, if you want to do an exhaustive search, you will have to pay the n factorial price to find the solution. TSP is probably the most popular and the most studied combinatorial problem today, starting with the mathematician von Neumann. And TSP has driven the discovery actually of many optimization techniques, such as, like Lagrangian relaxation, simultaneous annealing, and so on. So traditional solvers. So there are two classes of traditional solvers. We have exact algorithms where we get the optimal solution using exhaustive search, dynamic programming, or integer programming. And then we have approximate algorithms where we're going to trade optimality solution with computational speed. So usually for the approximate algorithms, we are going to have a simple rule, humanly handcrafted, and that we call heuristic. And for these algorithms, the complexity is usually polynomial, and we can measure the quality with respect to the optimal solution, and we have some kind of optimality gap. So for the exact algorithms, the first algorithm was designed was dynamic programming, and you have an exponential complexity, so you cannot really have too many cities. Then you have Jurobi, so this is a general purpose integer programming solver based on cutting planes and branch and bound techniques. And you have Concord, which is a specialized version of Jurobi. So it was designed by Tim Cook and his co-authors, and it's basically linear integer programming plus cutting plane and branch and bound. And Concord is actually seen as the fastest exact TSP solver available today. Okay, so TSP can be formulated as integer linear programming problem, such as this equation. So here you have the linear objective, here you have some linear constraints, and here you have the binary constraints that the x can only take two possible values, 0 if the edge doesn't belong to the solution, and 1 if the edge belongs to the solution. So you can have this interpretation of the equation for the linear objective. So you want to find the tour with minimum lengths, and you have the constraint that each city must be connected to two other cities like this. And this constraint is basically to be sure that if you take any set of cities and the complementary, you are going to cut the tour by at least 2 edges. If you don't cut by 2 edges, then you don't satisfy the feasibility tour. It means that you don't have a feasible tour. The problem, the integer linear programming problems are NPR because the space of solution is basically binary. So this is what makes the problem very hard. So what people did basically is to relax these binary constraints to a continuous space where you have a convex set of optimization. And in this case, you have a standard linear programming problem. The objective is linear. And then you have this convex set. Basically, you can rewrite these two linear constraints like this. And basically, it forms what we call a polytope. So this is the set of solutions. And then you are looking for, the straight lines, which is going, to be as close as possible to the polytope. So this will give you the solution. Solving a linear programming problem is actually can be done in polynomial time. But the problem here is that we need to solve for all possible S, such that you have a solution. But you can actually find many S that is going to violate these constraints. And so you must add more and more of these constraints into the linear programming problem to get a valid tour. This leads to the cutting plane techniques. It's basically the idea that you are going to add more constraints. For example, you are going to add these new constraints, and this will change the polytope. You solve again the linear programming problem, and you get this solution. But you need to do it, many times. So this basically is going to cost you a lot of time. The other issue is that when you solve a continuous linear programming problem, you don't have the guarantee to get a discrete solution to be 0 and 1. Usually you have a continuous solution. So for example, here the XE can be 0.6. And then you need to make a choice that are you going to include this in the solution or not? So this basically will introduce possible solution and actually a tree of possible solutions. And you can use a branch and bound technique to discard some tree in the search space by using some criteria where you can be sure that you don't get the optimal solution. Okay. So the overall complexity of Concord is basically the time that you need to solve the linear programming times the number of branches. So we don't know exactly theoretically what is this number. So what we can do, we can approximate this complexity. So what you see in dark is the Concord complexity, and what you see in blue is the polynomial complexity, and in red, the approximation with the exponential complexity. So for a small number of cities, Concord is a polynomial, approximate a polynomial complexity. But when you get, with larger number of cities, then you can see that Concord is going to have an exponential complexity. For the approximate algorithms, so the first one was the Christoffel algorithm based on the minimum spanning tree. Then there are insertion algorithms like a farthest and nearest or greedy insertion. And then you have the Google OR tools, which is basically a set of different heuristics applying to TSP and also a larger set of vehicle problems. Another class of approximate algorithms is based on TwoOpt moves. So basically, what you're going to do is that you are going to take, for example, here, 2 edges, and you are going to replace by 2 other edges to reduce the total length of the tool. Here you have here 3 opt moves. So when you consider 3 edges, so you have this recent LKH tree algorithms based on these K-opt moves, and which basically decide, the candidates to replace edges by using a minimum spanning tree. And this is today the best heuristic algorithms, which is available. So you can form a hierarchy of traditional TSP algorithms. Here you have the exactness. So it's basically between the approximate solution and the optimal solution. So you have the exact solution here. And then you get some approximation ratio between the optimal and the approximation. And here you have the speed of the algorithm. So this is the complexity. Exhaustive search, you won't be able to have too much cities. The same for dynamic programming. For Concord, Jurobi, with one computer like my computer, you can get to 2,000, but then you need a bigger computer if you want to get with a larger N. And then here you have the approximate algorithms. So recently, so we know that deep learning has significantly improved, computer vision, natural language processing, and speech recognition by replacing handcrafted, visual features by feature learned from data. So for combinatorial problem, the main question is whether deep learning can learn better heuristic from data. So better heuristic than what we humans we were able to develop so far. So this is quite appealing because we know that if we want to develop good algorithms to solve NP-hard combinatorial problems, this will take a lot of time and research. For example, TSP has been actively studied for 70 years. And we know that in industry, there are many problems that are combinatorial by nature. So the last 5 years actually have seen the emergence of new techniques based on neural network and graph neural networks to solve combinatorial problems with supervised or reinforcement learning. So I'm going to review quickly these recent techniques. So the first one was the Hopfield nets. So that's the old technique from 85. So that was the first neural network to solve very small TSP. Then there was the paper by Oriovians and his co-author, which is PointOrnate. And this is really, I think, the pioneering paper using modern deep learning to tackle TSP and other combinatorial optimization problems. It really open, you know, this class of algorithms, of deep learning algorithms, to solve these problems. So the idea is, okay, we are going to combine, you know, recurrent network to encode, you know, the cities using recurrent neural networks, and then we are going to start decoding, basically using again a recurrent neural network and attention mechanism to decide which is going to be the next city in the tour. Okay, so this is very familiar. So if you know NLP, this is very familiar with the paper by Dano, Cho, and Yoshua Bengio about translation, where they combine recurrent neural networks and the attention mechanism. So before transformer. Then there was an improvement of PointOrnate paper, which the learning was done with training TSP data. So it was done in a supervised way. Here, the idea is, okay, we don't use any TSP solutions because we know it's costly, you know, to have these TSP solutions. So we want to learn by reinforcement learning, by optimizing the length of the tour as reward. So in this paper, they use reinforced algorithms and then active search algorithms to explore the candidates. Then in this paper by Nazari and the co-authors, they improve the PointOrnate paper, because when you use recurrent neural network, then the order is important. And this is true for NLP, but this is not true for TSP. The order of the city is something which is not meaningful. So at the same time, it means that we need to enforce the network to learn the invariance with respect to the order of the city. So what they did is basically randomly permute the order of the cities in the original PointOrnate paper. So here they are order invariant. In this paper by Song and his co-author, they used a graph network that take as an input a graph and a partial tour, and then they estimate a Q function to know the next node in the tour. Training was done by reinforcement learning and memory replay, and also some heuristic based on the farthest insertion. Quadratic assignment problem, so the work by Johan Brunner and his co-author, so they cast the TSP as a quadratic assignment problem, and they use graph neural network to solve this problem, basically. So there was this work, permutation invariant Pauling network, where author solved a variant of TSP for multiple salesmen. The solution was continuous, so they needed to go back to an integer solution, and they use for that BiM Search. And interestingly, it's a non-autoregressive approach. It's done in a single shot. Then there was this paper by Louis-Martin Rousseau and his co-authors. Basically, they use the transformer encoder to encode the cities, and then they decode sequentially with a query composed of the last 3 cities. So they use actor critique reinforcement learning, and they improve the solution with the TwoOpt heuristic. Then there was the work by Max Wellin and his co-author. So they use a transformer encoder to encode the cities, and the query was composed of the first city, the last city in the partial tour, and the global representation of the cities. Then in this paper, we basically introduce a deep graph neural network, and we train by supervision. So by using training, by using TSP solutions to predict the probability that an H belongs to the TSP tour. And then we decode a feasible tour by using BiM Search. So this is a single shot technique. There is none. It is a non-autoregressive approach here. Then there was the TwoOpt learning. So remember the TwoOpt moves. You need to make a choice. So here people decided, to use neural network to identify the edges to swap. Okay. Then there was this technique combining graph neural network and Monte Carlo research. The idea is when you do autoregressive choice, you cannot go back if you make a mistake. So you want to be able to look at in the future, and for this you can use Monte Carlo research to explore different solutions before you make a decision. In this paper, they use a combination of supervised learning and reinforcement learning. First, they use the supervised learning technique that we developed in 5 to learn, an edge probability function that this edge belongs to the solution or not. And in the second step, they decode by using reinforcement learning and Monte Carlo research. They were able to get to a very large size for TSP, which is today, the best size of TSP with neural networks. And then there was this recent paper by Max Wellin and his co-author. Here they use again the edge probability map that we developed in 5, and then they decode by using dynamic programming with a specific TSP constraints, and they get the best supervised learning solution for 100. So now let me introduce our proposed architecture. So we cast TSP as a translation problem, basically. The input language is the set of 2D points, and the output language, so the target, is going to be the sequence of indices, which basically define the tool. So the motivation is, of course, transformer today is a very powerful architecture, and we wanted to see, if it was useful for combinatorial problems like TSP. We train by reinforcement learning, so we don't need any training set, with the same setting as the paper by Max Wellin. And the reward that we use is simply, the length of the tool. Okay, so here's the proposed architecture. I'm going to explain it. So we have a traditional encoder and decoder. For the encoder, basically, we're going to have as an input the 2D coordinates of the cities, and we are going to encode them using a standard transformer encoder. And basically, we will be able, to produce some vectorial representation of the cities where hopefully it makes easy the decoding, so finding the minimum tool. So we use a standard transformer encoder with multi-head attention, residual connection, and compared to the standard one, we use batch normalization, which works better. The complexity for memory speed is quadratic with respect to the number of cities. For the decoder, we are going to use an autoregressive technique. So we are going to decode one city at a time. So what I'm going to explain you in detail the decoder now. So suppose that we have decoding the first cities in the tour, and we want to predict the next city now. So we're going to have 4 parts for the decoding process. So the first part is basically, we are going to start decoding by using the encoding representation of the previously selected city. So for example, we have decoding already this partial tool. Okay, so we are at the time t, and the input vector of the decoder is going to be the encoding vector for the previously selected city with the index it. Okay, and we want to remember, the order of the cities. So for this, we use a positional encoding. We use the standard positional encoding in transformer, with sinus and cosine functions here. part two. So once we have the input vector for the decoder, what we're going to do is that we are going to encode, we are going to encode these cities by using the partial tour. We want to use the information of the tour that we have decoded so far. So to get this representation, what we're going to do, we are going to use a self-attention with between this vector here and all the previous cities before. Okay, so we use standard self-attention, multi-head attention, residual collision, layer normalization. The complexity is going to be the number of cities in the partial tool. Okay, and we are going to do that, for L layers. The next part is basically once we have, the query, which is based on the current city and the previous cities in the tool. Now we are going to, query the next city in the tool. So again, we are going to use the attention mechanism. So it's a kind of cross attention from, this city to the cities that have not been visited so far. Okay, so for this, we are going to use a mask of the cities that have not been visited. And the complexity, okay, is going to be N. The final part of the decoder will be to use, again, an attention mechanism, but this time we only use a single head. So for the last part, basically, we don't want to look at, multiple heads. We just want to look at, what is the next city. So just one head is enough. And then we get a probability distribution over the unvisited cities. And then from this distribution, we are going to sample the next city by using Bernoulli, distribution. So just flipping a coin. During training and during inference, we can use greedy. Okay. So if we want to compare the architecture for transformers for NLP in translation and TSP for combinatorial optimization. So first of all, for TSP, the order of the input sequence is not relevant. Okay, that's why we don't have any positional encoding for the encoder. But for the decoder, then the order of the sequence is important. And this is a solution. So we use, positional encoding for both TSP and of course for NLP. What we observe is that for the encoder, it's actually better to use batch normalization, because basically you are trying to encode, all cities in one shot. For the decoder, it's better to use layer normalization because we do autoregressive decoding. We are looking at one city at a time, so it's better to use the layer normalization, something independent of the size n. TSP for TSP transformer doesn't use any training data. We learn by reinforcement learning, so this is different from NLP. And finally, for both transformer for NLP and TSP, they have quadratic complexity, so this is n squared times the number of layers of your architecture. So if we compare with the most related models by Max Welling and Louis Martin Rousseau, so we use the same transformer encoder with batch normalization, and the difference is basically the query. So the query for the next city. So in our techniques, we query by using all the cities in the partial tour. And for Max Welling and his co-author, they query by using the current city, the previous one, and the first city in the tour, and the global representation of all cities. For Louis Martin Rousseau, so they use the last three cities as a query. So how also so the decoding process starts differently. So we use a special token city. So it's a kind of fake city. It doesn't exist, but this will give us, the best way to start the decoding. So Z will go through, the encoder. It will query all cities available, and it will basically create, a starting, city here. For Maxwelling, so they use as a starting decoding, they use the mean representation of the encoded cities and a random token for the first and the current cities. And for Martin Rousseau, they use a random token for the last 3 cities. The decoding techniques, so a tour is basically represented by a sequence of order indices, okay? And then basically you can cast the TSP as a sequence optimization problem. So you're going to have, the probability that the sequence is actually a solution of the TSP problem. And here you see that the probability is not as good as this one. So when you do autoregressive, basically, you can factorize the probability of the sequence to be in the TSP solution. Okay, so the probability that the tour from the first selected city to the last selected city, given the 2D positions of the cities, you can factorize it using the chain rule. So you have the probability of selecting the city, the first city, then times the probability of selecting the second city, given the first city, and so on and so on. So at the end, the problem is just maximizing the product of conditional probabilities, and this conditional probability is actually approximated by neural network. Okay, so once you have the probability, you can start doing the decoding. Exhaustive search will be factorial. Then you can have some approximate search, for example, greedy search. So at each time step, what you're going to do is that you're going to decide the next city to be the highest probability. So this is the fastest algorithm. So the complexity is linear. Or you can improve these sampling techniques by using, for example, BiM Search or Monte Carlo tree search. We know they improve solution for NLP and also for TSP, and the complexity is going to be n times the number of bins that you are going to use to explore the search space. So here we use a BiM Search. So I'm not going. I don't have time to go into the details, but this is very standard. So the numerical results. So here, this is TSP of size 50 cities. Here you have 100 cities. Objective is basically the length of the tour. The gap, this is the optimality gap between the approximate solution and the optimal solution. T time is for the training time, and I time is for the inference time. So training time, how much time is going to take to train, and inference time, how much time is going to take for one to decode only one city, only one tour. So here you have the mixed integer programming with Concord, which is for us, the optimal, solution. So the gap is 0%, of course. Then you have heuristic techniques, and here you have neural networks. So this is supervised learning by using training data. Okay, here you have supervised learning plus reinforcement learning. So these are today, the best technique for, I would say, for TSP larger than 100. And here you have reinforcement learning technique. So it's basically when you don't use any training data. And this is our model. So we are very close to the optimal solution for TSP 50 and also for TSP 100. And here we don't use any training data. So visually, we can compare the neural network solution with the Concord solution. And this is for 100 cities. So you see that in terms of length, we are close. This was an example. Then we can do some, zero-shot learning. So we use the network trained with 50 cities, and we look at, what we get for 100 cities. So we can see that if you use greedy, so just taking the maximum probability, so we get 3% gap. And then if we do BiM search, we get something 1.4%. So this is also zero-shot learning from 100 to 200. Okay. Complexity. So of course, so the blue is for neural network and transformer, and the dark is for Concord. So we know that we have exponential complexity for Concord, and then we have quadratic complexity for transformer. Discussion. So in this work, we essentially focus on the architecture. So we wanted to know if transformer was an interesting architecture, not only for NLP and computer vision, but also to solve these combinatorial problems. And we actually show that this kind of architecture is able to improve the reinforcement learning heuristic available in the literature. We have different ways to improve this technique. So we can have, of course, better sampling techniques. So once we have the probability given by the neural network, we can improve, we can improve the solution by looking at better the search space. For example, you can have group BiM search or Monte Carlo tree search. This is a way to improve, the solution. We know that. We can also use more heuristic, like TwoOpt heuristic to improve again, and also to get some intermediate rewards. What we do, basically, we only get the global rewards. We're just looking at the length of the tour and that's it. But here we can get some intermediate rewards and improve, the learning process. Okay, so everything looks, interesting and promising, but we need to be very careful. Actually, the traditional solvers like Concord and LKH actually outperform, neural network in terms of performance and also generalization. The complexity is better for neural network, but still, we don't do as good as the traditional solvers. So what's next? So there is something very special with combinatorial problems is that we can generate an infinite number of training data, but we cannot do that forever. So it's something also to be, to be careful. We can also probably improve further the architecture and also the learning paradigm. So learning is very different from NLP. So we can probably also, imagine some new and better ways to learn. Now we want to scale to larger TSP. We want to get to, for example, 1 million cities, but we have some limitation. We know that transformer, they are powerful architectures, but they are quadratic in complexity. So we get limited quickly with the GPU memory. So there have been some recent development like a graph subsampling and merging, which would be very interesting to move forward. We can also consider harder TSP like problems where the traditional solver like GeoB or LKH can only provide a rough approximate solutions or can take very long to solve. And probably something which is even more interesting is that we can go beyond the traditional solvers, for very complex combinatorial problems. So here we know how to do linear programming, linear objective. We know how to do quadratic objectives with convex, set. But what happens if you have non-convex objective, and non-linear constraint? That's something which is very hard to do with traditional solvers. But this is something very easy to do with reinforcement learning and this framework of neural networks. Another very exciting direction of research for that is that we can improve the traditional solver. So for example, branch and bound technique is very used in many combinatorial solvers. And the thing, you remember that we need to select sometimes the branch that we are going to explore. And this, can take a lot of time. So we have today some heuristic like human engineering heuristic, such as strong branching, but it takes a lot of time, to evaluate these heuristics. So there has been this recent paper, by Nair and co-author, and also Andrea Lodi and his co-author, where you can mimic, this heuristic and you can speed up, the process. So basically, the idea that each time you have to make a human decision, you can imagine to have a neural network, to improve this human decision. So as a conclusion, combinatorial optimization is really interesting because it's really pushing the limit of deep learning. Traditional solvers still work better than neural networks. but traditional solvers have been studying for a very long time, from the 50s. And the interest of using deep learning to combinatorial optimization has just started. So what we can see is that this topic of research will naturally, develop in the coming years, because combinatorial problems, again, are very important for companies. There is assignment problem, routing problems, planning problems, scheduling problems that are everywhere. And we would like, to have some, new powerful tools to solve these problems. So what I predict is that we will have some novel softwares that will combine continuous optimization, discrete optimization, and also learning techniques. So, for example, recently there has been, this paper by Andrea Lodi and his co-author, and also this software, which basically, try to combine, a neural network and discrete optimizations. So for this talk, the material, if you want to know more, so you have this archive paper. We also, made available the code on GitHub. You can try yourself, and there is also this article for general audience that you can see. One thing is, if you are interested in this line of research, so we organized recently a workshop at UCLA, which is deep learning and combinatorial optimization with really, experts in this field, and all videos are available on YouTube. So if you use the site, you can use this link as well. So I think my time is up. So thank you so much for your attention, and I am open to questions.
Thanks so much, Xavier. Fantastic talk. Really, really interesting. So now it comes to Q&A. Like audience members, please add your questions to the Q&A. As many questions as we can get is what we're after. And if you want to ask your question yourself, please put your hand up. And then we will unmute you so you can ask your question yourself. But don't put your hand up unless you're also adding a question to the QA, because you need to do both. Add a question to the QA and also put your hand up. If you don't put your hand up, you just give us a question, then we're going to read out your question for you. So now I'm going to hand over to Alessio and Giuseppe to facilitate the discussion.
Okay, thank you, Martin. Very interesting talk. There are many questions. So someone asked if this work can work in a transfer learning setting. I think you touched a bit upon it when you increased the size of the graph, but can you elaborate on this a bit?
Yes, absolutely. So of course, this is something that you would like to do. You would like your network to be able to generalize to different sizes, right? You would like, if you train on 50 or 100, you would like then to apply this to maybe 1,000 or 1 million cities. So I would say that some preliminary results are promising, because you can see, for example, if you want to double the size from, you learn your network with TSP of 50 cities, and then you want to transfer to size of 100 that you have never seen before. So you can get, something very close to the optimal solution. It's something like 1.4% of optimality gap. So you basically solve the problem in practice. The thing is, still, you can generalize, but not that much. So here we get from, 50 to 100, but the network will not work, like, for example, from 50 to 500. You cannot do that. The performance will degrade, very quickly. So that's really an open question, So how can we transfer to much larger sizes today? This is something which is an open question. It's not solved. It's not easy to do. And we know that, when you want to solve NP-hard problems, you have some kind of scale. So in some sense, when you change the scale not too much, like TSP 50 or TSP 100, the scale is more or less the same. So the geometry of the problem is more or less okay. But then when you get maybe to 10 times the size, then you have a problem of scale, and everything is going to break down. So it's really hard, and it's not really clear how to solve this problem. So what people try to do now is to subsample. For example, if you have TSP 1000, they try to subsample to, for example, TSP 100, and then they combine this subsampling. So they have many TSP 100. They combine them together to get the solution of TSP 1000. So that was a recent paper that I mentioned. Here. Yeah, so this paper here, this is the paper number 4. So if this is something which is promising, is that you can go to higher higher TSP sizes by using reinforcement learning. So this might be one way to go. Thank you.
Okay, thank you. Just a reminder, I encourage everyone, anyone that has a question, to raise your hands so they can ask them themselves. I think it's much better for discussion. Another question, which I personally find very interesting, and I was curious about this as well, is do you have any insight on what the network learns to perform better than other models, and if that operation can somehow be interpreted? The heuristics that networks find are interpretable.
Yeah, this is a question I have many times. So the interpretability of what the network learns. So some people did that. So in some papers, people try to look at the learned heuristic, how the network perform, the decoding step by step, and they try to compare, with a standard heuristic as well. So sometimes, you can get this interpretation, this, understanding of what the network is doing. So personally, I don't look at too much, the interpretation. I think neural network, there is a part we can understand. So for example, if you take convolutional neural networks and the first layers, so you can recognize, some patterns like Gabor functions that are very useful, to identify edges and texture in images. But then you have many patterns that, as humans, it's very hard for us, to understand what it's doing. So the Gabor function is something that we have used, before deep learning, and the performance of object recognition task was 25%, accuracy. Now with neural network, we get, to 3% error accuracy, but we don't understand, this pattern. So I think we can, look at a little bit, the heuristic learned by neural networks, but we should also be very careful that, they are usually better to find some, heuristic and patterns that is very hard for us to identify. But yeah, it's an interesting, direction. Question what they learn. Yeah.
Yep.
Thank you.
Thank you. And Samir has a question. They raise their hands, so I'm allowing them to talk, so you can ask it.
Hello, can you hear me?
Yes.
Is that working? Excellent. Sorry, it's possibly a bit of a naive question, but I thought it was interesting that the current architecture that a lot of is showing a lot of power in different places as the transformer and the attention mechanisms and so on. And here you've talked about, and thank you, by the way, it's brilliant. I love that you took the time to locate what you've done in the wider context, because it really helps people who aren't familiar with the problem space understand everything that people have tried to do. But so you've got situations where people are trying to fit the problem to the architecture, and you've had to sort of construct this really interesting sort of layered decoding phase with a number of different steps to try and make it work. But do you think it might go the other way at some point, that this combinatorial problems, because they're so peculiar, might inspire other architecture developments?
Oh, that's a very good question. I think so, yes. I think, so neural networks are very powerful, they are universal approximator. So they can approximate anything. The problem is not that. The problem is generalization. So if you take an MLP, you can, approximate any function. You don't need a transformer. You don't need recurrent neural network. You don't need convolutional neural networks. At the end of the day, you want to generalize. So how do you generalize? Is by having some, identify some specific data properties, or maybe specific, problem properties. And so, for example, for computer vision, one very important property is the translation invariance. And once you identify this, you know that the operator that you need is convolution. This is the way you can capture, the translation invariance in images. So that's the same for combinatorial problems. So what are the, the properties, the mathematical properties that you can identify and that are very useful, to solve combinatorial problems. So what we can do, as you mentioned, is basically going back to, the traditional solvers, try to identify some, strong maybe properties and trying to put it inside, the layers. So this is what people already try to do, so they look at, for example, the TwoOpt, algorithms, and then they try, to combine, this TwoOpt idea with, neural network. So I think this is something very important to go back and forth between what we have already designed, as a heuristic, that can be, some very powerful principles like convolution, but for combinatorial problems, and then trying to inject these principles, these properties inside the network. So this way you will get new architectures that will probably solve, better the combinatorial problems that you have at hand. And for different combinatorial problems, you have, different constraints, different properties. So that would be probably something very useful for generalization. Thank you.
Okay, there are a couple of questions that are about the data that's being used. So my understanding is that the data is synthetic, so it's automatically generated uniformly on the plane. And so if this is correct, have you tried with realistic data, and does that make a difference? Like, for example, like in real world data, you could have other factors other than distance between the 2 points, which might be maybe if a road is curved or some other things. So have you made the experiment? Are there any?
Yeah, that's a very good question. So so yes, what we use is basically, random distribution of the data points. So this makes the problem very hard in some sense, because you have no structure here. When you have random, distribution of points, then it makes, very hard, because you don't have any structure, to handle. So it's very hard for the network, to be able to develop some good heuristics. So if suddenly, you are using some real world TSP data, so you will have some more structure, So if you look at, for example, transportation networks, and the city has very, specific geometry, and then you want, to solve the TSP in this constraint environment, then probably you will learn much quicker than, having the training data to be randomly generated. That's something for sure that will improve. So yes, I mean, the training set that we use was just, synthetic, and I think it would be a very good idea, having, natural, I would say, natural training data, and see, how the network perform. Absolutely, I agree on that. Yeah.
Okay, just a brief follow-up. Do you think that you would need to add something to the network to make use of the structure, or do you think that the network will learn that by itself?
Yeah, so absolutely. So what you can do is that you can add something to the network easily. So for example, if suddenly, so here, I didn't put any graph structure. So the graph can represent, for example, the transportation network of your city. But that's very easy to do, because a transformer is a graph neural network. So you can add, in the attention mechanism, the graph structure. And then suddenly, again, you will get a better generalization performance. So if you have, again, some prior distribution about the domain, so for example, a graph, then you will improve the performance because it's more constrained.
Right. Okay. Thank you. And then some people asked about BiM Search. So Christoph asked if, like, make an observation that a BiM size of 1,000, which you had on one of your last slides, seems to be very large for the problem at hand. And so does this computational time come close to the exact solution when you have a BiM, like when you use a BiM search with that large number? I think it was a couple of slides after this.
Oh,
but yeah, like that as well.
So maybe for the generalization, I'm not sure.
Yeah, like when you go to larger problems, you also use a BiM size of.
Yeah, maybe this one. Okay. Yes. So here, for example, you have the time. This is inference time. So if you have Concord, it's going to take 1.3 seconds. If you have neural network and a BiM search of 1,000, it's going to be 1 second, which is already faster than Concord. So of course, I mean, BiM search, whatever BiM search or Monte Carlo tree search or any your favorite search algorithms, you're going to have BIMs for sure. So this is very important. You want to explore the space of solutions. And what a neural network gives you is basically, just a guide. It's just going to give you how you're going to explore the space. But at the end, you need to rely on this standard, search algorithms like Monte Carlo tree search or BiM search, to explore the space and extract, some solution. So I would say that for 1,000 BIMs, it's nothing. 1,000 is absolutely nothing. The speed is already faster than Concord, so it's absolutely nothing. But you don't get the exact solution. So in recent papers, people use 1 million BIMs. They use 1 million BIMs, to do that. So if you use a lot of BIMs, this is good because you are going to have better solutions. But at the same time, you cannot use anymore the autoregressive techniques. Because autoregressive technique means that you are going to decode city after city. And it means that for each query of the next city, you will need to call the network. And calling the network means going through the GPU. So it's going to take a lot of time. So you don't want to do that. So recently, there was the paper by Max Welling basically trying to decouple, the query of the network from the search space. So basically, they first have a first part that is going to learn, to learn an edge probability, so which is based on our paper, and then from that they just use the probability for each edge to be in the TSP solution, and then they use a standard dynamic programming or BiM search, to decode the tour. And this way, because they don't call the network, they can have 1 million BIMs of search. So that's something. I think 1,000 is nothing, and if you want to go to more, then you need to be very careful that you don't want to call too much your network, because it's very GPU intensive.
Okay, thank you. And I think we are out of time now because it's 7:30. So thank you for the discussion, and I will let Martin perform the final.
Thank you, Alessio.
Sorry, I'm on mute. Thanks, guys. Thank you so much, Xavier. Really wonderful talk. Thanks so much for the discussion. Thanks to the audience for the great questions, and thanks to Alessio and Giuseppe for managing things on the Zoom and for facilitating the discussion. So like I said, if you have any ideas for future speakers, please get in touch. But let me just close by thanking once again Xavier and to say goodbye. Thank you very much.
Thank you very much, Martin, for the invitation. Thank you so much.